Yeah, let me get this set up. Okay, so it's, hold on 1 second, sorry. Here it is. They do not have you on this list. Okay, so it's quadratic. What else do we know about this function? Concave down. Before we even say concave down, though, there's something else that we should recognize about it. Hold on 1 second. All right. All right. So, all right. So, what were we saying?
Quadratic, concave down.
Okay, but before, so I would agree, and I would start with the fact that it's quadratic. That is important. But guys, we got to go beyond quadratic very, very, very quickly. So let me write the equation here. H of x equals -2 times x minus 3 squared minus 8. So it is quadratic, yes, but come on, beyond that, if we want to identify some features of the graph, we got to recognize that that's vertex form. P.S. What is that vertex form? A times? Well, okay. Okay. So vertex form, we've got that vertex form written out. So what features should I know about that vertex or that quadratic function very quickly then? What's negative? Well, so what is negative that tells us it's concave down? So A. A is less than 0, concave down. We should recognize that immediately. What else should we know about this function? The line of symmetry. What is that line of symmetry? X equals 3. Because that comes from x equals h, which h is that part of the vertex. I will say there's something that, like, if it's vertex form, we should, like, very quickly jump on. The vertex, right? What letters in the vertex form represent the vertex? H and K. So my vertex is 3, comma, -8. Now, Jamarcus, can you tell us why it's a positive 3 right there? Because I see x minus 3. Remember, it's x minus h. We need to switch that sign, right? So it's always going to be the opposite with that x value. So the vertex is 3, comma, -8. Does anyone know anything else about this function? Has what? Has 2 zeros. How would I find those 2 zeros? Okay, but how? Okay, so maybe the zero product property, but before we can use the zero product property, that function has to equal what? 0, right? So let's say 0 equals, I'm looking for 0, so what is h of x going to be? 0, and I get -2 times x minus 3 squared minus 8. So look at that again. Can I use the zero product property? What form does it have to be in? Not standard. Factored. Well, I will say, sometimes we took standard form and we factored it to use zero product property, but we have to get to factored form because literally we need a product. We need to recognize the form here. It's a vertex form, so what can I do to find those zeros? I can use inverses with properties of equality. When you have vertex form, you need to immediately recognize, hey, I can use inverses with properties of equality. So what would I use? How would I go about solving this? What's the first inverse I need to use? Okay, why the +8? Right, when I read this, x is being subtracted by 3, then x minus 3 is being squared, and then x minus 3 squared is being not quite, because remember you said subtracted by 8 is the last thing. Remember the order of operations. We did parentheses first, then we did the exponent, then what comes after that exponent? multiplication by -2, even though it's in front, that's the next piece. Then after the multiplication is -8. Pay attention to your order of operations to know what is the last operation being done so that you can undo it. -8 plus 8? 0. Great job, guys. Yay. 8 equals -2 times x minus 3 squared. Now what? So divide by -2 or multiply by that 1 divided by -2, right? Okay. Right here, you see how this is being multiplied?
Yeah.
What's the inverse of multiplication? Division.
Oh, I know that, but I'm saying like.
Why use that fraction? So I always recommend the fraction because students freak out whenever it's like a 3/4. We don't want to divide by 3/4, but if I just use the reciprocal, that creates a 1. So I want you to practice using that reciprocal all the time because it'll help you in every situation, not just some. But that's the same thing as multiplying by 1 divided by -2. Like, what is 8 times 1? 8 divided by -2 is -4. So it actually is a very useful way to do that division instead. It's what I wish more teachers would start doing. Now, what do I need to do? Square root. What's the square root of -4? So it is a positive and negative, but we do need to recognize that to I. Remember, square root of -4, that's the same as square root of -1 times 4. That's the square root of -1 times the square root of 4. So we split up those factors to things I can take the square root of, and the square root of -1 is I. There we go, good job. Square root of -1 is I, square root of 4 is 2, which I get a positive -2i here. So notice, will this graph intersect the x-axis? No. Those are imaginary zeros. Okay? Add 3, add 3. So, 3 plus or minus 2i equals x. So, I want to remind you that when it's vertex form early on, we were supposed to quickly identify the vertex and quickly identify the concavity, but now that we know more about solving quadratic equations, you can set that equation equal to 0, but pay attention to the form to know how to solve it. If it's already in vertex form, what can we use? Inverses with properties of equality. If it's in factored form, we're going to want to use zero product property. And if it's in standard form, we're going to have to either factor, convert to vertex form, or use the quadratic formula, right? So those are things we got to recognize. We have to recognize the form so that we know the strategies we can use, and you think through those things. Last thing I will point out is, could I find the y-intercept for this function? How would I do that? So a2x is y, but I said the y-intercept. So remember, for an x-intercept, the y is 0, but for a y-intercept, the x is 0. So I can always easily find the y-intercept. So you should be able to find every feature of a quadratic function no matter what form you have. That would come out to be a 9. That would end up with a really negative number, negative 26. So there's your y-intercept. Okay? What are your questions about identifying those different features of a quadratic? That really reviews like a unit and a half worth of ideas. But that's supposed to be a pretty solid review for what we are doing. Okay. Now, one of the major reasons why I wanted this bell ringer is because I also wanted to tie this into the inverse stuff we've been doing. If I have this function right here, that's the same as y equals -2 times x minus 3 squared minus 8. If I were to ask you to find the inverse equation, what would you have to do? This is going to help you prepare for the understanding check we have today. So I need to use my inverses, right? If I am asking you to find the inverse equation, this input needs to become my output. So I need to undo all the stuff around it. So what am I going to do first? Plus 8. What was the first thing we did over here? We added 8. The last operation being done is the first one I need to undo. So then I get what on the left-hand side? So 8 plus y, or traditionally we would write y plus 8. I would accept either one, right? We're just adding those together. Equals negative 2 times x minus 3 squared. Now what? So multiply by negative 1/2. That's the last operation being done this time. And so you can literally just leave it like that. I would completely accept this notation. Do notice I have parentheses around it because I am multiplying that entire thing. Now what would I need to do? Notice how this is exactly following this exact format. This is not anything brand new as long as you keep in mind, hey, I need to solve for x. Now what? Add 3? And I would write that 3 either in front or behind, it doesn't really matter. So x is equal to 3 plus or minus the square root of negative 1/2 times y plus 8. Now I want to show you something that is really useful about this inverse equation. If I'm looking for a 0, what's that y value again? 0. Hey, what's 0 plus 8? 8. What's negative 1/2 times 8?
Negative 4.
Negative 4. What's the square root of negative 4? If you have the inverse, it's really, really easy to just substitute a number in for y and find what x is. That's one of the powers of that inverse idea, is that when we have the inverse equation, I can just substitute my y in and get the x out very quickly. And I can do that for any y value now. So instead of having to solve the equation every single time, like instead of putting an 8 here and solving for whatever x would be when y is 8, I could just substitute in and find that value. What do you mean? No, this is done. I'm just pointing out, if I wanted the zeros, it'd be really easy to find now. That's my only point there. Now, we'll point this out. Is this currently a function? One input has how many outputs? Hey, shine. What would I need to do to this equation, though, if I wanted it to be a function? Restrict the domain. And remember, we would restrict our domain. One thing I would point out about this equation, we've identified all those different features, right? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So 3, negative 8 was our vertex. That was where our line of symmetry was. There's no x-intercepts because it's going down, right? What would I need to restrict my domain to be so that my inverse would be a function? What would I need to restrict the domain to be? You're good. You just need to restrict one side of it, though. So let's just say I erase this side. What would my domain now be? It's the left-hand side, so it would be going from negative infinity, right? It's going down and to the left, so the domain would be negative infinity to, remember, these are domain values. What's the maximum x value? 3. Right? Just looking at the graph, I can figure that out. I could have restricted it by just looking at the right-hand side. And if I take out the left-hand side, what would my domain now be? What's my lowest x value now? The lowest x value? Starts at 3 now? And what's the maximum x value? Infinity. See how it keeps going to the right? So, those are the things we want to consider and keep in mind when we're thinking about quadratics, when we're thinking about our vertex form and all those different things. What questions do you have before we continue with today? Okay? Remember, I cannot answer a question that's not asked. So, what is math? Oh, I forgot to update this agenda. But what is mathematics? It's that study of patterns and relationships. All of these things are patterns that we need to learn and we need to notice and understand. We need to understand that when we have that vertex form, I'm going to use my inverses with my properties of equality. That's a pattern that shows up time and time and time again. The inverse, right, is that reflection across y equals x. That's a pattern that we want to notice time and time and time again. We're actually going to, look at lesson 2 just briefly. I need to check to see if there's anything in here that we need to cover. So we actually reviewed all that. One thing that we didn't get a chance to look at here, one thing to remember is what's happening to the domain and the range of the function and its inverse. They're switching because the inputs and outputs are transposing, right? So don't forget, we have see that time and time and time again. So I'm just going to briefly look here at activity 2.3 with y'all. This is on page 28, thank you, in 3-28. So we've been working very heavily with the cubic function, or with the quadratic function and its inverse. What's the inverse of a quadratic? Square root, right? Excuse me, volume 2. So we've been working very heavily with that quadratic and its inverse, the square root. Now we're looking at a cubic function in activity 2.3, and we can just quickly graph these points. Pay attention, right? -2, -8. Now I do want to point out, where in the world is that point coming from? They're not just making up these points. Where did -2, -8 come from if we're dealing with a cubic function? Come on. Where's -2, -8 coming from if we're dealing with a cubic? Huh? Yes, I know it's in the table, but how did they get that in the table? It's not random. How did they get -2, -8 in this table if we're dealing with c of x equals x cubed, a cubic function? Do we not know, or are we not trying to think about it, just trying to avoid the question? Jayla, what's -2 times -2 times -2? What's -2 times -2?
Power 4.
Mm-hmm. Times -2 again.
-6.
4 times -2 is -8.
8.
So what is -2 cubed? -8. The way we get a table is we substitute our inputs in and get our outputs out. The next point is -1, -1. How are we getting that? Well, what's -1 times -1 times -1? These things are not random. They are the inputs and their respective outputs. And so then we graph 0, 0, 1, 1, and 2, 8. And I want to point this out. So we have this little graph right here from those points. Is this cubic invertible? What do I mean by that? Well, I don't mean that it passes the horizontal line test. A horizontal line test is how we check it. But what does it mean to be invertible? The inverse is still a function. And we check that with the horizontal line test. So is this function invertible? Yes. It passes that horizontal line test and details like that. Now, we haven't dealt with a cubic and its inverse, but I will point this out. What is the name of the inverse of a cubic? But I thought square root was the inverse of a quadratic, an x squared. So the inverse of a cubic would be a cube root. Have you ever sketched out a graph of a cube root function before? Really? Where? I was like, I don't think so.
I thought we did do that one.
Which one? When?
When we were learning about cubic.
When did we learn about cube roots?
You went over it.
Yeah, you did.
Yeah, I do remember some of that.
I thought we did, maybe we did do a reflection of y equals x cubed in the last lesson, but we didn't really talk heavily about cube roots. Maybe you're right. Regardless, do you know points on the cube root function? Does anyone know a point that would be on the cube root function? Where'd you get -8, -2? You transposed your x and y.
Yeah, you told us about that.
-8, -2. Inverses, no matter what, we're transposing the x and y. So what's another point on our cube root? -1, -1. Another? 0, 0. 1, 1. And then 8, 2. So inverse functions do not have to be complicated. We need to remember that they are transposing the inputs and the outputs, and that they are reflections across what? Reflections across y equals x. So, transpose your inputs and outputs. What points do the two graphs have in common? Yeah, why would all three of those be in common?
They got the same.
You're right, keep going. Same what?
They got the same, like,
So they have the same input and output, right? And so when we transpose them, they are the same. And also remember, they are located on what important line? Y equals x. They're on the line of reflection. Right, so the inputs and outputs, when we transpose them, will be exactly the same, and they are a reflection across y equals x. So those are things we want to notice there. Make sure you have your original y equals x cubed and the inverse. Okay? And so I will point this out. They already told us the equation up here. We good? Not for real? Because of the math, or just one of those days? Sorry, bud. Please notice here, they are already using this notation. What does this notation mean? Because we didn't use this originally with quadratics. When we see this notation, it is the inverse, but not just the inverse of the function, it is the inverse function, right? Meaning that the inverse is also a function. We only use this notation when we have an inverse function, right? That superscript -1 tells me the inverse function. Notice we do not have a positive or negative. Why not? Well, it is already a function, but also look at the original, or look at the inverse there. Is it already a function or not? It is, so each input only has one output. Remember with that quadratic, how it was like this, so each input had two outputs. When you take a square root, you have to do a positive or a negative. But if I ask you for the cube root of 8, that equals 2. Could it equal -2? Does -2 cubed equal 8? No, it equaled -8. So notice there's not two inputs for each of those outputs, so there's not, so we don't need positive and negative with those cube roots. Right? We don't need to restrict the domain because the inverse is already a function. Okay? Then this is the last detail before we do the understanding check. The inverses of power functions with exponents greater than or equal to 2, such as the square root function, the cube root function, are called radical functions. Literally, that's because, so like this would be a fifth root, but this little symbol right here, you know what it's called? Radical. That's why it's called a radical function. That specifically is the fifth root, but it's called a radical function for that reason. So, just a little bit of mathematical language for you there. We'll talk about this after the understanding check because it's not there. Alright. Clear your desk except for a calculator. I need to, yes. I'm going to be working on that today. I was just already up till 11 o'clock last night. There's only so much time in a day.
Oh, I didn't check it.
Haley, clear your desk. Okay, the plan is that what we know you should be able to show within 15 minutes or so. So I'll check back with you 15 minutes, but guys, don't just sit there and stare off into the sun. Go ahead and clear off your pencil or whatever pen you used to do the assessment. Grab one of the G2s that's in front of you. There should not be any pencils on the desk. One of the things that I will remind you is pay attention to the details to make sure that you update or fix the things that you made mistakes on. And you can still show some evidence of understanding even with making mistakes. And that's what I'm looking for, is evidence of understanding. So here's what I did for that first function, or for the first two questions. Do notice if you are correctly restricting the domain, you're taking out that whole left-hand side so that you get a function that passes the horizontal line test. And notice that the inverse stops right there. It does not go past. It stops there, just like this parabola stops at the vertex. Okay? So, we did not go to the left of here. The domain stops here, which also means, I would point this out, what is the range of f of x? What is the range there? We're going to see it in a second, but what's that range? What's the lowest y value? -4. What's the maximum y value? So what should the domain be for our inverse function? -4 to infinity. You cannot go to the left of this. So pay attention to that. Make an update if you need to. What questions do you need to ask about the restriction of the domain or how I got that inverse function? Say again, Haley? Okay. Hopefully this is something where we can learn from it. We can update and quickly understand how to fix things. Horizontal line test. That is in the textbook, Module 3, Topic 1, Lesson 1. So if you look at Module 3, Topic 1, Lesson 1, you'll see information about the horizontal line test. That was something that Ms. Estel covered last Thursday, and then we went over Friday, Monday, and Tuesday. I know some of us are writing information down still. As you write and you think about these things, do we have any burning questions? Do also note with the graphing of the inverse function, what did I create to help me show evidence of understanding? A table. That table's really helpful, guys. Okay. So here was my number 3. Right? Solve for x so that the input becomes my output. I've shown that conceptual understanding. And then if I'm going to solve that equation so that I get x equals, what am I doing? Just like in the bell ringer, I'm using my what? Inverses. If I need to, do I need to write it up here so we can see it more clearly, Marshall? Do you need me to write it up here? Okay.
Can you do it difficult?
Then orange? And so one thing I will point out, I've written it on there, notice when I take this square root, I get a positive and negative, but would this be a function? No. But remember how we restricted the domain? So I no longer would actually have the positive and negative because I've restricted the domain. I would only have the positive, which is why that's what you see at the end. So x would equal the square root of y plus 4 plus 3. That plus 3 is outside of the square root. And then remember, if you need to transpose at the end so that you can graph it. I would say to get a 4 plus, yes, but as long as you justify things well, no. The reason why I would say yes, Naisha, is notice I did ask write the equation for the inverse function, f1 superscript negative 1, right? So I asked for that inverse function of f1 of x. So I was looking for that notation because we now do have a function. You couldn't use that notation if we didn't restrict the domain, but because I restricted the domain and I got just these positives here, you would have an inverse function. Any other questions? Especially questions about how or why I did things. Okay?
But I don't have a question.
Yes, ma'am.
Why would you do, it's just an inverse, why would you do plus 4? Like, f of x plus 3 squared plus 4, why would you do that?
But, well, because remember, if I want the inverse function, I need to use my inverse operations. What you said was x plus 3 squared plus 4?
Like, you wouldn't do the opposite?
Well, two things with that. The opposite is only one type of inverse. Notice I did use the opposite, right? But one thing that to remember is what was an input needs to become an. So you see that minus 3? I do need the opposite, but because that was the input, it actually needs to be a part of the output, right? This part that was the output needs to become a part of the input, and the inverse of a square is a square root. Just use your inverse operations, right? So don't just write an equation with the opposites. You need to recognize that inputs and outputs are being transposed, but the easiest way to do that is to use your inverse operations to solve that equation. So does that make sense, Eliza, why the 3 is now on the outside, the 4 is on the inside, but again, the square root as well. So I would use my inverse operations to solve that. Notice domain and range, how I identified and explained how I got them. I will say you could, if your domain and range match your graph, I will account for that in your scoring. But one of the major things that we should have noticed, what happens to our domain and range? They switch. That's one of those foundational things. That should be a positive 3, not a negative 3. Sorry. So that positive, so the domain and range should switch. Notice the order of the domain and range don't switch. It's not infinity to 3, it's just what was my domain has become my range. What was the range became the domain. And I made that note, domain and range switch for the inverse. And we can see it in the graph. How what? This right here? That's the notation for the inverse function. So like if that, so I didn't write what the inverse function was, but if f1 of x is this, we just found the inverse function over there. That's the square root of x plus 4 plus 3. But that's the notation for the inverse function of f1 of x.
What's it say under continues? What's it say under continues?
Under which part?
The middle, it's the middle section.
Right here?
Yep.
Continues forever, right? So I was pointing at this infinity. Why is the domain in 3 comma infinity, right? So that's the minimum x, and then it continues forever to the right. That's why the x goes to infinity, right? So I'm identifying those min x, the min y, or the minimum x, the maximum x, the minimum y, the maximum y, things like that. Okay. Any other questions? I see a handful of us still writing things down, so I'm going to wait a second. But any other questions? Hopefully we at least knew enough to now look at this and see where we can improve our understanding or where we need to ask questions. Alright. So there's a lot here. There's a lot more than you necessarily need to earn like a 3D plus or maybe even a 4. But these are all the things that I thought about when I thought about functions and their inverses based on what we have explored. Like the first sentence there is the most important. You had to know that inverses are reflections across y equals x, so inputs and outputs transpose. To get to the 3 level, to show me clear evidence of understanding, you had to have that first sentence. The rest of this is also important information about what an invertible function is, what we learned with the even degrees and the odd degree power functions, things like that. Any questions with any of that, or does it look pretty familiar? And hopefully we got all of it or next to all of it. Push all of your understanding checks to the center of the group. I'm going to come by and collect them during the first little bit of the activity. Go ahead and make sure they're turned the same directions. I'm going to make scans while we work through this next little bit. Go ahead and get your textbook out. You want to turn to M3-107. We are actually moving to the next topic that is going to apply a lot of the information that we have been studying, okay, into a new context. We are moving away from, hear me clearly on this, We are moving away from radical functions, but we are still focusing on inverse functions. So on the unit test, we will still have the inverse functions information, and we will still have the radical functions information that we've studied. Where's the other thing? But we will also have this look at something called exponential and logarithmic functions. So right in there. All right. So, yeah. 106, is that what I said? 107. N3-107. Sir? I actually meant to update groups, but I totally forgot. We will do it Monday. Meant to do that while y'all are taking the understanding check. I don't know why I did that. Yep. I thought I already answered that. Did I not? I thought I said go quickly. Alright. So, what type of function are we exploring within this lesson? It says exponential. So we're going to look at exponential functions, not for very long because we've already explored exponential functions, but there are a couple of things that I do want us to think about with exponential functions. And instead of doing the book way, which is a very static way of just writing things down, I have a calculator file that I created. So pick up your calculators. It actually helps when I name it. Sorry, let me save this real quick. Exponential functions space exploration. All right. In a true Mr. Kinney fashion, this file is just all about noticing patterns and relationships. So, what I want you to do, you can't see this yet. Okay. You should have gotten the file now. What I want you to do is I have set the values of b between, I believe, -1 and 3. And the values of b can go by 0.1. So click on these arrows to go through the different values of b, and I want you to look for some patterns and relationships. That's it. What do you notice about the values of b as you explore and go through those different things? Take a little bit of time to look at it on your own and then start talking with your small group about what you see. That one. Hit enter. That one. And then, no, don't say it. Just hit enter. No. Okay. So once you played around with it for a little bit, what patterns do you start to see? Talk about within your small groups. Did not pop up. Remember when it doesn't pop up, go to browse. Okay, so talk with each other, look at all those different b values, look for some patterns and look for some relationships. Nope, that's why I did that. I know, we'll talk about it. So come on, what are some patterns, what are some relationships we're noticing? Huh? I know, right? Yeah, that's weird, isn't it? Oh, by the way, guys, I should have reminded you of some exponential function language. We have two different shapes for exponential functions. Does anyone remember what they're called? They're exponential growths. So it is an exponential curve for all of them, but it can either be an exponential growth or an exponential, starts with a D. Not decrease, but it does, close that, huh? decline line makes sense, but no. You have growth and you have decay. Okay? So exponential is growth and decay. So try using that mathematical language for patterns that you notice. So what have y'all noticed about the exponential growths and decays?
Wait, what is decay?
So look for some values of B. What do you think the decay would look like?
I don't know the I have never calculated.
Okay, why don't you go to a value of B to show me when you think it's decaying, and then we'll talk about it.
It's decaying right now.
Not quite.
When it goes from left, when it goes to left, and then
Keep going.
also it's
So there is this weird thing where it starts to split and it looks really funky.
yeah.
Yeah.
Like he goes to left.
Oh my gosh.
It's supposed to be.
What did we notice? Okay, but we need some more than just that. Think about that exponential growth and decay idea. What patterns do we notice? When is it exponential growth? When is it exponential decay? When could it probably, when is it just weird?
Yeah. Look at this.
I know! Look at that! What is that? You ever seen that before? Same. Actually I have, but it's a little funky.
So,
Let me ask you this, do you think that's an exponential function? It looks like that?
It's weird when you
Interesting. So think about when it's not an exponential function. Okay, what are we noticing?
They turn into like, hey, these supposed to watch.
Yeah. Does that look like any exponential function we've ever studied? So let's use some mathematical language. Talk about when it's the function is not going to be exponential then. I'm just asking you when is it not exponential. I'm not asking you what this is. I'm asking you, looking at this, when does it appear that the function is not exponential? Okay, but think about it. You're manipulating that value of B. What values of B? By the way, guys, listen. If this hasn't been clear, we need to recognize that the B is what's controlling that exponential function. So you need to be thinking about patterns and relationships in respect to B. What is B? When is the function exponential decay? When is it exponential growth? When is it none of the above? It decays when what? So which B values are making it decay?
No, there is something when it
Don't just say less. Which ones? The specific values that we want to look at. Huh?
It's like yes.
When it's a single digit, so when it's between what two numbers? So you're, because I would say you're thinking like 0.6, 0.8, right? So what number, there's two numbers that we would say that's in between. Between 0 and 1, and then we get to that something funky, right? Yeah. Does that look like any exponential function you've ever seen? So when are we not looking at an exponential function? Think about that. Okay, so 1. Okay. We're going to come back together in probably about 60 seconds. So finish your discussions. Think about what values would create different situations. So what's happening? So you say growth is bigger? Bigger than what?
No, like, bigger one.
So if the B is greater than 1, it's a growth. If it's less than 1, is it decay? Is it always a decay when it's less than 1? Okay, so when it's 1, it's a line. What about if it was 0? It's nothing, so it's not an exponential. So those are things we want to discuss and consider. Okay? Thank you. Thank you. Okay? So we should be noticing some patterns and relationships, right? This is a quick way to explore these exponential functions and understand them better. So I need some conjectures. I don't think I've actually confirmed anybody as being 100% right or wrong. I just need ideas generated. What are some things, some patterns that we have noticed? What is that? When did you see something that you didn't know that it goes like funky?
It starts at
Point two?
and then it gets worse.
You sure it's at point two?
See, look, Jay, look, that's a point eight, that's what it does.
That's a negative point two.
You may hide out.
I'm pretty sure that B value is negative.
Yeah.
Okay, so ladies and gentlemen, anybody see something funky like this?
Yeah.
It looks weird. So what, there's some language I use with some of us. What does this not even look like? Not just not a function, it is really funky, but specifically with the functions we're looking at, it doesn't look like a what? Okay, but what does it not look like with the functions that we're studying? It doesn't look like an exponential, right? You're saying a curve, but it doesn't look like an exponential function. The whole thing is to explore exponentials. So what we're starting to notice is some values of b don't create exponential functions. So if b is what, it's not going to be exponential. So we do not have an exponential function if b is what? When it's what? When it's negative? So are there any negative values for b that have exponential functions? No? At least through those, there's definitely not any. I'll go ahead and confirm you. That's a good pattern to notice. B is not exponential if b is... How could I mathematically write that it's a negative? What in respect to 0? Yeah, b is less than 0. We don't have an exponential function. Did anybody notice any other values for b that didn't have exponential functions? 0 itself? Oh man. Yeah, when I look at b equals 0, that is definitely not exponential. So it is not exponential if b is less than or equal to 0. Say that again. Let's look at 1 as well. Ah, man. If b is equal to 1, it's not exponential as well. And that should make sense. If I have f of x equals 1 to the x, what is 1 raised to any power? It's 1, right? 1 to the second is 1. 1 to the third is 1. 1 to the fifth is 1. Right? So a b of 1 is not exponential. A b of 0 or less than or equal to 0. So guess what? For an exponential function, b can't be less than or equal to 0. Or equal to 1. So b cannot be less than or equal to 0, and it cannot be equal to 1. Hey, what's going on? Because we need to learn, we got to get focused. What's going on? You lost your what?
Is that
It won't close though.
it?
You gotta worry about your ear closing.
Okay. Let's let Sanaya look, but the rest of us need to focus. So, what are the two types of exponential functions that we should be looking for? An exponential growth. What does an exponential growth look like again? Can someone come up here and just do a quick sketch of an exponential growth for me? Ethan, come on with it. Remember, as graphs move left to right, that's how we read a graph. The graph needs to be growing. What did we notice for an exponential growth? B needs to be what? Let's check that. If b is greater than 1, are all those functions growing? Yep. I will point this out. Like right now, b is a 2.1. And I bring that up because originally, I get this, someone said, if it's a decimal, then it's decaying. But notice that's a decimal, right? So it's not just about whether it's a decimal. As long as b is greater than 1, it's growing. Because what happens if I do 2 times 2? I get 4 times 2 again, 8 times 2 again, 16. Those numbers grow whenever b is greater than 1. So when is it going to be an exponential decay? Sure about that? This is close, but there's an issue with this. Because if b is less than 1, look what numbers that would include.
Oh, negative.
That would include 0, it would include the negatives. So can b just be less than 1 for an exponential decay? No, it needs to be less than 1 but greater than 0. So b needs to be between 0 and 1. Notice, to be an exponential decay, that's the shape of it. To be an exponential decay, b needs to be between 0 and 1. What are your questions about these details? I'm going to show you somewhere to write this in your book, but can we visually see this? Does this make sense about that value for b? About how we get an exponential growth or decay? Going once. Going twice. Means it's sold. Okay. So, we do need to note where we are in the book, because notice we skipped lesson 1. We skipped a whole lot of lessons from the last topic, because we have to focus on the most important things to get us to the end of the semester. We did lessons 1 and 2 out of the last topic. We are starting in lesson 2 with this topic. And we are looking at properties of exponential graphs. And we're going to learn about a new, really important number called e here in a second. So first things first though, if you go to the end of activity 2.1, this is where we're going to summarize what we've learned. Number 4, summarize the characteristics for the basic exponential growth and exponential decay graphs. First things first, where you have space there, probably in the side, I would sketch out a quick sketch of an exponential growth and an exponential decay. Okay, that's going to help us in a second. One thing I need you to pay attention to is this. I was very intentional about it, and Ethan did a pretty good job of it. Does this exponential ever actually get to the x-axis? No. Do not let your exponential get to the x-axis. It doesn't do it. It approaches, but it never quite gets there. The exponential function approaches the x-axis, but it never gets there. Because here's the thing. Let's say I have 0.1, and I raise it to the x. If I repeatedly multiply it by 0.1, I get a positive times a positive times a positive times a positive, which means that this will always be what kind of number? But more importantly, if I multiply positives for forever, I get a positive. Does it ever get to 0? No. Does it get close? Heck yes. That's why I say it's approaching. But it never gets there because I'm continuously multiplying by a positive number. So it never gets there. Now, be careful and pay attention to that. So summarizing this information, and this is going to matter for when we start studying the inverse of this exponential. What is the domain for the exponential growth? Notice they already defined that b has to be greater than 1. What is the domain for that exponential growth over there? Not quite. Eliza, remind us, what does domain refer to?
Something about x.
Yeah, something about the x values, right? Yeah, 100%. So it's a set of all x values that's ever existed. So what is, looking at that graph, what's the minimum x? What is the lowest x value I can substitute into that equation? Negative infinity. Notice it keeps going to the left for forever in the x direction. What's the maximum x value? Infinity. It goes up, but it also goes to the right. And it's the right portion that we care about for domain. Okay?
What page is it?
110, yep. It's the end of activity 2.1. So now I look for the range of the exponential growth. Range is referring to what, Tevin? What's the range refer to, my man? Tevin, this can't be a question. We got to know instantly. When I say the word range, we're thinking about which values? The y values, the outputs. Remember, domain is my x or inputs. Range is my Y, or outputs. You gotta instantly know that. That is not something we can have a question about. We gotta instantly know that information. So range, I need the minimum range value. What is it? 0. Now, I want you to think about this. A lot of times when we've had actual numbers, we put a, what symbol with it? A bracket. But we talked about it. Does that ever get to the 0? No, so can I put a bracket on it? No. Well, that's just when we have the parenthesis. If that number is not actually in the value, if we don't ever actually get there, we can't use a bracket. We use a parenthesis. And then what's the second number for that range? Infinity. And this is a word that I introduced a couple days ago, that word asymptote. Remember, we defined it in the last topic. This is a, and we're just use a line now, but a line, the function approaches at an infinity. That could be a positive or negative infinity. So can I get someone to come up and just circle where we think on the exponential growth that we have an asymptote, a line that that function is approaching? So go up to that exponential growth. Where do you see a line that that exponential growth is approaching? Exponential growth. Okay? Anybody want to push back on or add on to that, or ask a question about that being the line?
Why you think that? Why you think that? I don't really know.
Just guessing?
No.
So then you have to have some idea of why you put that.
Do you think? I don't know. I
Do you-
kinda disagree.
You disagree? You want to change it? Okay, so let's see what Naisha's thinking. Okay? So what line do you think that is that it's approaching?
Huh?
What line is that?
Oh, wow. Oh,
Is that is infinity a line though?
no.
Mm-mm.
So ain't no line.
No, there's definitely a line that it's approaching. It's when it gets flat. So I would have looked here.
Ain't that about
You see how that's a line? That's a line that that function approaches at an infinity. It doesn't have to be a positive infinity. As x goes, and I want you to think about this, for our end behavior, that's a great way to think about it. And it comes up in a second. As x goes to the left, what is y approaching? Mm-mm. It's flattening out, getting close to what y value? 0. You remember how we said our range was 0 to infinity? And so as x goes to negative infinity, as we go forever to the left, y is getting close to 0. So you know what our asymptote would be? Y is equal to 0. The x-axis. If you want to circle that x-axis there to show, right? Circle that x-axis there to show that that's the asymptote. And maybe note that, or identify it, like write that out.
How do you spell asymptote? Right here on your paper.
Yo.
Oh, I didn't see right here. My bad. So all this asymptote.
Huh? Be on the test, yes.
Ooh.
Intercepts. I will point this out. What key type of intercepts do we not have? We don't have x-intercepts. But do we have a y-intercept? Yes, Mr. Kenny. We do. Now, you may not know what this is right away, but I want you to think about this. What is the x value on the y-axis? X is equal to 0. So for a y-intercept, x is equal to 0. What is anything raised to the 0 power? Nope. 1. You don't remember that detail? Okay, so let's remind ourselves of this detail. If I have 5 to the second, what does that mean? No, what does it mean though? 5 times 5. Right? 5 to the third. Yeah, because everyone's like, yo, Mr. Kenny, an exponent means repeated what? Multiplication. However, here's a detail that we are forgetting. If I have 5 to the first, I only have a 5. There's no multiplication there. Unless we remember that we actually are starting with a 1 times 1 5. 1 times 2 5s. 1 times 3 5s. So 5 to the 0 is still 1 times, not 0, we just don't have any 5s, times 0 5s. Jalen, can you let whoever that is in? So we don't have any 5s that we're multiplying by. In the same way, b to the first is 1 times b, so b to the 0 is just 1. So if I'm looking at the intercepts here, all I have is a y-intercept of 0, 1. And we already talked about the left-hand side in behavior. As x goes towards negative infinity, right, what is y approaching? 0. So on the left-hand side, as x goes to negative infinity, y goes towards 0. On the right-hand side, what is x approaching on the right-hand side? Keeps going to the right, doesn't it? So as x goes to infinity, y is going towards infinity. Remember, we're only looking at the growth right now, but that is it. We didn't really do intervals of increase and decrease, so ignore that for now. Actually, don't scratch through it, because we might come back to it. Sorry, I don't know why I did that. That was silly. We might come back to it. Alright, basic exponential decay right here. Here's my decay. What's my domain for this? The lowest x value is negative infinity. It keeps going up, but it also keeps going to the left. So the lowest x, negative infinity. The highest x, positive infinity. Because it's going to the right. So remember, domain only refers to x, right? So furthest left, furthest right. What about that range then? What's the lowest y value? It's still 0 again, isn't it? And what's the highest y value? Anyone see an asymptote? So, well, the x-axis, again, which is when y is equal to 0. Do we have any y-intercepts or x-intercepts? No x-intercepts. It never hits the x-axis. But we still have a y-intercept of 0, 1. Anything to the 0 power is 1. In behavior, left-hand side. What's x approaching on the left-hand side? If we're going to the left, x goes towards negative infinity. And what's the y going towards? It's going up towards infinity. Right-hand side, as x goes towards infinity, y is going towards, notice it's flattening out, going towards that 0 on the right-hand side. That's why we have that asymptote there. So I apologize for the speed of that. Make sure you take the time to look through this information. I see Miracle, hold on 1 second. Look through this information, make sense out of it. Over the weekend, we'll come back and start with activity 2.2. So learn about the number e, and then quickly jump into the inverse of exponential functions. Yes, sir?
E is a letter.
Huh? It's also a number. Did you know that pi is a letter?
Yeah, 3.4.
No, that's a number.
What's an asymptote? 3.4.
So, pi is a Greek letter, and we use it to represent 3.14. So, Miracle right here. Asymptote is the line that a function approaches at an infinity. So when we look right here, as we go to the left for forever, you see how it's getting close to the x-axis? So it's a line that it's approaching. It never gets there, but it gets real darn close.
Okay.
Oh no! Hey guys, come back for your understanding checks later. I forgot to make scans. I will make scans, come back for them. And yeah, I saw the email. I don't think you were here today. I was going to tell you. So what happened was when you loaded it, I don't know what you loaded or what you did, but it basically looks like you took a picture of your thumb and a picture like that uploaded. There was no file there, right? So that was the issue. But I saw that you said you emailed it to me.
Did you file my own essay?
Did you email it to me?
Yeah.
I don't remember finding it, but I will look for it. Shoot me an email to remind me to look for it though, because otherwise I could easily forget.
I'm so tired of school.
Me too.
See how that nigga man puts his album back?
Good morning, Kason. Yes, sir. Good morning, Kanye. Good morning, Kanye.
Okay.
There we go.
What you been at, Jamarcus? Oh,
Good morning, Jamarcus.
okay.
Yes, sir. Good morning, Inslee. Yeah, you are.